Okay, so picture this. You're steering a ship that's worth hundreds of millions of dollars down a river that's, well, it's alive. It's constantly changing. The channel you need to follow shifts. The water level can rise and fall by meters. And every single decision you make is a massive, high-stakes bet. Today, we're going to pull back the curtain on the hidden science that turns this incredible risk into a calculated and very profitable journey.
This quote right here really sets the stage perfectly. Think about it. A printed map of a living, breathing river is basically a lie the second it's printed. The sandbanks are moving, the depths change with the seasons. So, yeah, the chart is a starting point, but it is nowhere near the whole truth.
And that's the big question, isn't it? That's the central conflict. When the static chart in your hand doesn't match the dynamic, unpredictable river right under your keel, how do you move forward safely? Well, the answer lies in turning old static data into new predictive intelligence.
So this brings us to the core problem we're trying to solve, navigating a river of uncertainty. And, in the world of modern logistics, uncertainty isn't just a minor inconvenience. No, it's a direct threat to the bottom line. Every single unknown variable equals risk, and risk always costs money.
This whole massive, complex game of river navigation, it really boils down to this one single critical measurement, under keel clearance, or UKC for short. This is your safety buffer. It's your breathing room. And if you get this wrong, you're not just late. You could have a grounded vessel, a potential environmental catastrophe, and a completely blocked waterway. It is that critical.
So here's the issue in a nutshell. Your nautical chart gives you one number for the depth, but the river doesn't care about your chart. That depth is a constantly moving target. Seasonal floods or long droughts can change the actual water level by meters. Relying only on that chart is kind of like trying to navigate using yesterday's weather report.
So, if the map is wrong, how do you fix it? Well, the answer is to fight back with technology. You start treating the river not as a static picture, but as a dynamic system that, believe it or not, can actually be predicted.
And the solution starts with this really beautiful, simple concept. You take the fixed depth from the chart, and you add what's called a dynamic corrector, which is just the actual measured level of the river right now. This simple act of addition transforms a static piece of paper into a live, dynamic navigation tool. It's brilliant. So how is this correction actually calculated? Well, first, you have sensors all along the river. They're called gauge stations, and they collect real-time water level data. Then, some pretty smart algorithms correlate that data to project the water level exactly where the ship is, or, more importantly, where it's going to be. But the real game changer is that last step. Statistical models can actually forecast that river level weeks into the future.
And this is where you really see the commercial power of all that forecasting. These systems can predict the river level 20 to 30 days out with a 95% confidence level. That means a shipping company can know with incredible certainty the conditions their vessel is going to face a whole month from now. And that lets them plan their cargo load with absolute precision.
But predicting the water is only half the story. You also have to predict how the ship itself is going to behave in that water. And this brings us to a fascinating distinction in how you do that. Think of it as the hammer versus the scalpel. This is all about calculating a phenomenon called squat. It's kind of weird. As a ship moves, it displaces water, creating this low-pressure area underneath it that literally sucks the hull down, making it ride lower in the water. And the faster you go, the more you squat. It's this invisible force that is actively eating away at your safety margin.
Now, there are two main ways to calculate this squat effect. First, you've got the hammer. It's a simple, quick method that's very, very safe because it overestimates the effect. But that conservatism has a cost. It forces ships to carry less cargo just to be safe. Then there's the scalpel, a precise, surgical calculation for detailed planning. It considers the ship's unique shape to maximize every last bit of cargo safely.
And you can see the difference pretty clearly here. The hammer is a blunt instrument, low complexity, but it always overestimates. The scalpel, on the other hand, is a surgical tool. Yeah, it's high complexity, but it is incredibly precise. It allows a cargo planer to use software to figure out the maximum safe draft right down to the centimeter.
Okay, so we've got the river prediction and we have a precise squat calculation. But these are just two variables in a much larger equation. Now let's see how all the pieces of this dynamic safety puzzle fit together. So, the next variable is heel. It's really just pure geometry. When a ship leans over from a strong wind or a sharp turn, one corner of its hull naturally dips deeper into the water. This seemingly small tilt can instantly eat up precious centimeters of your clearance.
And then, of course, you have waves. A ship pitches front to back and it heaves up and down. These motions are just relentless in rough water. A good rule of thumb is that these combined movements can steal clearance equal to about 1/3 of a wave's height. So a 3-meter wave could be invisibly taking a full meter of your safety margin without you even realizing it.
And here it is, the final equation, the whole shebang. Your real, safe under-keel clearance is simply what's left over. You start with the total water you have to work with. That's the charted depth plus the current river level. From that, you have to subtract everything that's taking up space. The ship's own draft, plus all those dynamic factors we've just talked about. Squat, heel, waves, and yeah, even the density of the water matters. So why does all this complex math really matter? Why do we obsess over these tiny little variables? Because in the world of global shipping, every single centimeter of water translates directly into tons of cargo, and that means revenue.
This number right here is just staggering. During the dry seasons, when river levels are naturally low, if you're relying on those overly conservative hammer calculations, you could be forced to reduce your cargo capacity by up to 50%. You are essentially sailing a half-empty ship, all because of uncertainty.
And this is the payoff of precision. Economically, it's a no-brainer. You maximize your cargo on every trip, you get more flexible departure windows, and you cut down on costly waiting time. But just as importantly, you guarantee safety. You prevent groundings, you make sure the ship stays maneuverable, and you turn the great unknown of the river into a known, manageable variable.
This quote absolutely nails it. This technology isn't just about better math. It's about a total shift in philosophy. It takes that margin of safety, which is really just a margin of ignorance, and it converts it directly into profitable cargo capacity without compromising safety one little bit.
And that leaves us with a final question to think about. We've just seen how data can tame the chaos of a river, turning a huge physical risk into a logistical opportunity. It really makes you wonder, in our super interconnected world, what other invisible forces, what other rivers of uncertainty, are just sitting out there waiting to be mapped, predicted, and transformed by data?